Welcome everyone to our video on molecular orbital theory. This video will effectively conclude our Unit 4 discussion looking at advanced theories in bonding, where we're basically going to be building up the theory that allows us to understand orbital structure in sort of the most general sense. So we'll start by looking at very simple molecules, but the same concepts will apply to very large molecules such as this, where we're effectively going to be building up the tools to understand how electrons exist in these more complex structures. Okay, so first up here, when we're talking about molecular orbital theory, there's a couple things to keep in mind, and I like to go back and sort of do a quick summary here of where we've been when we've talked about valence bond theory and the concept of hybridization. So remember, when we built up valence bond theory and we talked about hybrid orbitals, we certainly added something to the discussion from our previous discussion of Lewis structures, in the sense that we brought orbitals into the conversation. However, we were still a bit artificial in the fact that we confined electrons to atomic orbitals, okay, or hybrid orbitals more generally, right? So confining electrons to atomic orbitals isn't very accurate, because if you recall, atomic orbitals come from solving the Schrodinger equation, okay? Now, we need to be careful there, because the degree of accuracy really boils down to the specific application at hand. There are, in fact, many examples of molecules where the actual orbitals that you would get from solving the Schrodinger equation for a given molecule, right, and we'll call those orbitals molecular orbitals, may very well look like atomic orbitals, or what we saw in our previous lecture video, okay? However, you don't necessarily know this a priori, okay? And so what we want to do in this unit here is essentially build up the tools that would allow us to discuss molecular orbitals more generally. And the power of being able to do this is quite significant, right? If we were able to determine molecular orbitals for a general molecule, we would be able to predict any property of that molecule. And I'd like to draw your attention back to something we discussed back in Unit 3, when we were discussing Schrodinger's equation and its applications to atomic structure. There is a very famous physicist, Paul Dirac here, who said, a quote, basically following the advent of quantum theory, that the underlying physical laws for the mathematical theory of a large part of physics and the whole of chemistry are completely known. But the problem comes down that the exact solutions, in this case, determining those MOs, right, leads to complicated mathematical problems that we simply can't solve very easily, okay? And modern computational chemistry is actually rests on molecular orbital theory in many ways, in the sense that we use more advanced concepts related to what we're going to be talking about in this lecture video to actually solve cutting-edge problems in computational chemistry, to predict material properties, to design new drugs, and a lot of very interesting stuff. So the foundation here that we are going to be laying is certainly highly relevant to sort of cutting-edge chemistry. Now, the problem here, right, and again, referencing back to our discussion in the previous unit on atomic structure, remember that as soon as you move to a system that is, say a neutral helium atom with a proton and 2 electrons, we are met with the challenge that we cannot solve the Schrodinger equation directly. What we have to do is make approximations. And so the core concept behind molecular orbital theory is that we are going to make an approximation that basically serves as an educated guess as to what the solution might look like. And then we are going to introduce some techniques, mathematical techniques, that allow us to essentially optimize that solution, to essentially make it better. And we'll talk about what that means here in a second. And once we have that approximate solution, what we can do is essentially start solving other problems and predicting molecular properties, okay? So what we're going to do here is use a little simulation. Again, we're not going to dive into the mathematical details here, but we're going to use a little simulation to explore what on earth I'm talking about by when I say you devise an educated guess and basically optimize this guess to come up with a better and better approximation to the molecular orbital theory description. So the approach that we're going to be using here, it's all based on a theorem in quantum mechanics that says that no matter what we choose as a guess, we can never do better at minimizing the energy than the true molecular orbital. Okay, so we could pick any random guess you want that satisfies certain conditions, boundary conditions, and details aren't as important here. But basically, we can pick any well-formed guess and we can modify that guess such that we minimize the energy. And the lower we minimize the energy, the better that guess will be in terms of representing what that molecule actually looks like. And so the guessing approach that we are going to use here is the so-called linear combination of atomic orbitals approach, or LCAO approach. And what we're now going to jump over and do is look at a little simulation that applies this linear combination method to a very simple molecule, H2. So we can see here, H2 molecule obviously is comprised of one helium atom or hydrogen atom and another hydrogen atom brought close together, right? Close enough that they're in bonding distance. And we are going to approximate the molecular orbital for this simple system in a very similar way that we did in our last discussion, talking about valence bomb theory. We are going to essentially make a guess that is a function that is represented by the sum of 1s orbitals on both the hydrogen atoms. So in this case, the guess function here would be the 1s orbital on the red hydrogen atom plus the 1s orbital on the blue hydrogen atom here. Of course, the color coding is just to help us, keep things straight in terms of what I'm talking about here. And we're going to basically just say, okay, our guess function is just going to be the sum of those two atomic orbitals. Okay, and this is what we mean by a linear combination, right? We're just adding up individual atomic orbitals, and we are going to weight each one of those atomic orbitals by a coefficient, okay? And for our purposes here, it would be just some real number. And we're going to denote those coefficients C1 and C2. And so what we'll do now is jump over here to our simulation. Okay, there we go. So you should see here on the screen this little simulation that is, just reproducing what we had on our lecture slide. But what I'm doing here in this simulation is now I'm able to modify the values of each one of these coefficients, C1 and C2, the weighting, if you will, of the respective 1s orbitals on each one of the hydrogen atoms. And so I'm going to just sort of pick one of these and sort of move it around a little bit. Okay. And you can see by modifying C2, some interesting things are happening here. Specifically, this orange line that we're dealing with here is representing the energy as a function of bond distance between these two hydrogen atoms. And by making these coefficients larger, notice that the size of the orbitals that are being depicted here, representing the 1s orbitals, are increasing. Okay, so you can think about basically if I multiply a function by a number, that gets larger and larger, then that entire term gets larger and larger, and that shows up as a heavier weighting of one of those orbitals here. And so notice that as I'm changing those values, this orange line on the curve here that's representing energy as a function of distance between the atoms is changing itself. Okay, so if I go down here and I'll put it back, the orange line is way up here now, and if I move it back to where we had it, both of them where the orbitals are overlapping nicely. Now that orange line is getting lower, and notice that as I make these orbitals a little bit bigger, we're ending up with a higher degree of orbital overlap, and the orange curve is approximating the black curve. And the black curve is actually the experimental value. This is sort of the our best knowledge of the energy of the energy of the H2 molecule as a function of r, the distance between the two atoms. And so you can see that we're basically moving around our values of C1 and C2 to get that orange line as close as possible as we possibly can to that black line. And there's a couple things, again, the procedure that we use in practice would be, obviously not consisting of little sliders here, but we use numerical methods to optimize, these functions and the energies, right? But for our purposes, I just want you to sort of understand the core concept here. We are changing coefficients, making a linear combination of atomic orbitals, changing coefficients to get these the predicted energy orange lower and lower and lower and lower. And the better we can do that, the more accurately it will represent the black curve here, which is the true energy. And of course, in practice, we don't know the true energy, otherwise we wouldn't be doing this. And so the process just basically boils down to finding coefficients that minimize the energy. And you'll notice here that because H2 is a symmetric molecule, if we do anything that introduces asymmetry, like one orbital is larger than the other, then the energy gets worse. It gets higher and higher here, further away from the black. And so that's effectively what we care about in terms of our starting point for our discussion here, for discussing bonding. And it's something where it's going to be, increasingly important, is perhaps if you went further on in your chemistry studies to understand the numerical methods. But for right now, we're going to just leave it at that. And we're going to, sort of look at some of the results, similar to what we did back in our discussion of atomic theory, where we said, okay, hey, look, we've got a pretty good idea of, what these orbitals look like, because we can approximate Schrodinger's equation very well, or solve it exactly for hydrogen, and sort of using those results, and just sort of focus on the big picture. We're going to do the same thing here, okay? And so the pictures that I want you to carry around in your head are something as follows, right? We use this LCAO, linear combination of atomic orbital approach, to give us a simple yet fairly accurate guess, right? And by building up weighted sums of atomic orbitals, we can make new orbitals like we saw in our simulation. And in the case of the simulation, and what I'm depicting here again on this next slide, is a weighted sum of two 1s orbitals that gives us a larger orbital where we are increasing electron density between the two atoms, right? And we call that a bonding orbital. And what we're effectively doing is increasing the three-dimensional space that these electrons have to move around in, rather than having little electrons that are existing in these electron density or orbitals isolated on individual hydrogen atoms. Now these little electrons are described by the probability distribution that's spread out over both of them. And the result is a lowering of the energy. So we look at increasing energy on the y-axis here, moving up. We see that forming this bonding orbital actually lowers the energy, right? And if we remember, in valence bond theory, orbitals were weighted sums of valence atomic orbitals that were just on a particular atom, okay? But the key idea there back in valence bond theory was that these hybrid orbitals remain localized on an atom, right? And in MO theory, we are looking at weighted sums of AOs on all atoms in the molecule. So we're no longer localizing the electrons to individual atoms. We are making molecular orbitals that are linear combinations of all atoms in the molecule, or atomic orbitals on all atoms in the molecule, right? And this is more powerful, right? We're now forming molecular orbitals that are delocalized on the entire molecule, right? And as we saw previously when our discussion of Lewis structures, delocalizing electrons, remember resonance, think about resonance, delocalizing electrons results in a lowering of that energy, all right? So in our example of the H2 molecule, the MO formed from the overlap of the two 1s orbitals, giving us this bonding orbital. is our sort of first guess approximation of what we think the bonding orbital looks like for H2. And we have some special names that talk about this sort of bonding arrangement. So this MO, this molecular orbital, is called a sigma 1s. So Greek letter sigma with a subscript 1s. And the reason we call it that is because it looks like a sigma bond. Again, remember back to our valence bond theory. Okay, it's symmetric along the axis connecting the two nuclei. And we call it a sigma 1s because it's formed from the overlap between two 1s orbitals. And of course, the sigma 1s orbital is lower in energy than the isolated 1s orbitals, and we therefore call it a bonding orbital. All right. Now, here's the thing, okay? When we add two orbitals together, we got that bonding orbital. But there's other options as well. If we take those two 1s orbitals and say subtract the two, okay, so take the difference between the two, you're basically taking two orbitals and adding them together, but one of them is out of phase, okay? And the result of this sort of combination where you're subtracting orbitals or taking this out of phase combination is a situation where you create a node. Remember, a node is a region of space where there is zero probability of finding the electron. And by forming a molecular orbital using this out of phase combination, we are effectively making what we call an antibonding orbital, because in this antibonding orbital, we are actually decreasing electron density in the region between the two nuclei. And we're decreasing it to a very extreme extent. Right in between, there's actually a node. There's zero probability of finding an electron there. And so this is obviously still a sigma-looking orbital. We still have that symmetry across that internuclear axis. And we are still building this MO by taking the combination of 1s atomic orbitals. But because we are taking that out of phase combination, we're making this antibonding orbital, we're decreasing electron density between the nuclei. We need to denote that, and we denote that using a little asterisk here. So the star, as we call it, is denoting an antibonding orbital. So we would read this as sigma star 1s. So anything with a star denotes antibonding. All right. Now, the thing to remember now, right, is there's basically a sort of rule of thumb here, okay? When we are making linear combinations of atomic orbitals, okay, we have a sort of conservation in terms of the numbers of orbitals that we have, right? So what I mean by that is if I take a linear combination of two atomic orbitals, we will get two molecular orbitals. And we saw that previously in the last two slides. Taking the sum of the two 1s orbitals gave us our sigma 1s bonding orbital, and taking the difference gave us our sigma star 1s antibonding orbital. All right. And so bonding orbitals, the key characteristics here are listed in the following bullet points. We're going to see lower energies than the constituent atomic orbitals. We are seeing constructive interference between the AOs, right? That's illustrated here, a buildup of electron density in that internuclear region, that region between the two nuclei. Conversely, antibonding orbitals, shown right here, have higher energy than their constituent AOs. They're characterized by destructive interference between the two AOs. Remember, we even get a node right here in between. And this decrease in electron density in the internuclear region really motivates the entire name for antibonding. If a bond is a buildup of electron density between the two nuclei, well, if I'm decreasing electron density between the two nuclei, it's the opposite of bonding, so we call it antibonding. So to sum that up, we can make what we call a molecular orbital energy diagram. So in practice, we don't draw out the little 1s orbitals and do something like this and then add them together. What we do is we write out an energy diagram, right? Very reminiscent of what we did back in our unit on electronic structure theory for atoms, right? We talked about the energy of the orbitals and we populated electrons accordingly. a lot of that same, in fact, we're going to be using all of the same machinery we used back in our previous unit. Now we're just extending the concepts to that of a molecule. So in the context of a molecule, we need to talk about bringing together orbitals with specific energies on adjacent atoms. And the bonding orbital, remember we saw it lowers the energy, is going to show up on the energy diagram as a lower energy, in this case, sigma 1s orbital, and a sigma star 1s for the antibonding. All right. Now, as soon as we make our molecular orbitals, we need to do a little double checking. Remember that we need to conserve the number of orbitals. If we have 1, 2 atomic orbitals coming in, then we're going to be making 1, 2 molecular orbitals, right? So that all looks good. And then once you've made your molecular orbitals, your final task is to distribute electrons. And so we have these orbitals coming in this case, hydrogen has 1 electron in each of its 1s orbitals. We have a total of 2 electrons, valence electrons, that are going to be populating these molecular orbitals that we are building. And so we're going to follow the same rules we did back in our previous unit. We are going to put the electrons in the lowest energy orbitals first, making sure that we're spin pairing them, following Hund's rule, all that fun stuff. And so if we do so, we find that with a sigma 1s orbital can, of course, as all orbitals, accommodate 2 electrons as long as they are spin paired, one spin up and spin down, and that utilizes all the bonding electrons. And so we see that the H2 molecule forms because you get a molecular orbital that has 2 electrons in it, and we could call sigma 1s, that has a lower energy than the isolated atoms by themselves. Now, this gives us a way that we can start not only predicting what bonds are going to form, what molecules are going to form, but also the strength and sort of magnitude of that bonding interaction. And so we quantify this using a concept called bond order. So bond order, very simple expression here. All we do is we look at our molecular orbitals, the center part of our MO energy diagram, and we count the number of electrons in the bonding molecular orbitals. That'd be this guy right here. And then we're going to subtract off the number of electrons in the antibonding molecular orbital. We're going to divide it by 2, and we're going to calculate the bond order in that way. So for H2, we of course have 2 electrons in bonding. We have 0 electrons in an antibonding. So 2 minus 0 is 2, divided by 2, we see 1, a bond order of 1 for the H2 molecule. So a positive bond order implies that more electrons are in bonding orbitals, and hence a net lowering of the energy upon bond formation, and thus we would predict that this molecule would in fact form, which is no surprise. We already know that H2 is a very common molecule. And so this is the cool part here now, is we now have some machinery that can describe for us in a much more rigorous way why we don't see certain molecules forming. So the next example here is the helium-2 molecule, He2, where we again have electrons in 1s orbitals on isolated helium atoms. If we bring those 2 helium atoms together and once again form molecular orbitals, a sigma 1s and a sigma star 1s, just the same sort of framework that we did for hydrogen, now we have a total of 4 valence electrons that need to populate those molecular orbitals. And so we're going to put our 2 in the bonding, then the remaining 2 in the antibonding. And if by populating equal numbers of bonding and antibonding orbitals here in terms of the total electron count in each, we find that the bond order is going to be 0, right? And if you have a 0 bond order, we would predict that a bond does not form between these atoms, which of course is what we observe experimentally. Helium does not bond with other atoms in general. All right. So even more powerful predictions that we can make from MO theory are more exotic molecules that maybe you haven't thought about before. So in some cases, you can even predict molecules that would exist that we don't know they exist until later on we go to experiment and test them out. And so that's one of the powerful aspects of computational chemistry and using molecular orbital theory. So to get a flavor for this, let's look at a very simple molecule, helium-2 plus. So same sort of story as helium-2, but now we're adding in a positive charge, which means we're taking away one of the electrons. So we imagine one of those helium atoms only having a single electron. When you form your MOs, populate the bonding and antibonding, we see that there is only one electron in an antibonding. So you can pause the video here if you'd like and try and calculate what the bond order would be for He2 with a positive charge. Okay, so let me get a page here. When you do that little calculation, we are going to be getting bond order equal to the number of electrons in the bonding, which is 2, minus number of electrons in the antibonding, which is 1, divided by 2, which is 1/2. So we predict a bond order of 1/2, which means that we would expect to be able to observe this molecule. Now, it's not a particularly strong bond, and it might not be a particularly stable molecule, but MO theory does predict that the helium-2 plus ion does exist, and in fact, we can observe that experimentally. All right, so what have we done so far? Right, the basic idea behind linear combination of atomic orbitals, MO theory, is that we can approximate MOs, molecular orbitals, as linear combinations of atomic orbitals. The total number of MOs formed from a particular set of AOs always equals the number of AOs in the set, right? If I bring 2 atomic orbitals together, I get 2 MOs, right? And remember, combining AOs is done in 2 ways. You can add them and subtract them. When you add them together in phase, we get a new molecular orbital that is lower in energy, and bringing together out of phase results in a higher energy antibonding molecular orbital. Right? When assigning electrons to a molecule, we're always going to follow our rules from our atomic structure discussion. Fill lowest energy MOs first with a maximum of 2 spin paired electrons per orbital. If you have 2 MOs of the same energy, apply Hund's rule, put 1 electron in each before pairing them up. And the bond order is the number of electrons in bonding minus antibonding divided by 2, right? Stable bonds are associated with a positive bond order, more electrons in bonding MOs than antibonding MOs. In general, the higher the bond order, the stronger the bond you're going to be dealing with. All right, so that sums up our introduction to molecular orbital theory. In our next video, we will look at some more advanced examples of MO theory, looking at diatomic molecules in the second row of the periodic table.